Kính thưa thầy, nhóm em xin phép nộp video demo luận văn tốt nghiệp. Em xin phép được bắt đầu. Today we would like to present our graduation project entitled PCB Surface Defect Detection and Classification using Xor-Based Localization and CNN Model. Our project is supervised by PhD Pham Khoa. Our group include Nguyễn Binh and me, Nguyễn Phúc. In this presentation, consider 5-part introduction, Xor-Based Defect Localization, CNN-based defect classification, experimental result, and conclusion. PCB are critical component in modern electronic system. Even small surface defect can strong affect product reliability and cost. So AOI systems are widely used. They still face accuracy and robustness issue. In this work, we focus two main challenge. First, PCB defects are small and visually subtle. The second, real PCB datasets are limited and imbalanced. To address the issues, we propose to study PCB inspection framework. First, defect regions are localized using iso-based reference comparison between template and test image. The second, extractoid are classified using CNN model. In this separation enable fast localization using classical image processing and accuracy classification using deep learning on smaller ROIs. We use iso-based localization to avoid full image deep learning detection. To improve CNN robustness, we apply regularization techniques as L2 penalty dropout as well as ROI level data augmentation. This test image show many defect type detected and classified. After introducing the motivation and overall solution, I will move to second part, the presentation, which focus on ISO-based pre-processing for defect localization.
My name is Nguyen. My student ID is 21161229. And for the next part, I'm going to talk about the XR-based pre-processing for defect localization. So we use a reference-based method by comparing a defect-free template image with a test image and pixel-free pixel level differences indicate the possible defect regions. And this works well for bare PCBs because defects often appear as a small changes on copper traces and paths. Next. And direct comparison is sensitive to shift and rotation. So firstly, we align the images using ORB feature matching and homography. And then we apply binary thresholding to both images and compute an XOR difference map to highlight mismatch regions. Right after that, we use morphological operations to reduce noise and extract connected regions to generate bounding boxes. And each box is cropped into fixed 64 multiply 64 ROI for CNN input. Next. And each ROI is classified by the ResNet number based CNN. Finally, we export the defect label and bounding box coordinates for visualization and reporting. Next. And after localization, we focus on defect classification. We start with the most simple one. We called the simple CNN baseline using 5 blocks of convolutional layers with 2 activation layers, ReLU and max pooling right after where the number of channels gradually increases. The classifier uses to fully connect layers with the dropouts to predict 6 defect classes. This is lightweight. This the model is lightweight, so it may miss subtle defect patterns. And to get stronger features, we tested deeper models. Like the next one is DenseNet. It uses the dense connectivity to reuse the features and improve the gradient flow. So this is often helpful when the data set is limited. So we also evaluate ResNet 50, which is built from residual blocks with skip connections. Skip connections make deep training more stable, and ResNet 50 can extract stronger features for complex visual patterns. However, the ResNet 50 uses pre-trained backbone, so it can fit a small ROI dataset too easily and cause overfitting. So to reduce this, we apply regularizations like dropout, L2 penalty, also called weight decay, and using learning rate scheduling to stabilize training and improve generalization. And now I will explain a bit about these methods that we used. The first one is batch normalization. It basically normalizes the activations within each mini patch, then applies learnable scale and shift. This helps training become more stable and converge faster. The next one is L2 regularization. It adds a penalty to large weights controlled by Lambda, and this encourages smaller weights and helps reduce overfitting. Next. So beside the model regularization, we also use data augmentation before training. This increases diversity from limited ROI images and makes the model less sensitive to small shifts and lighting changes. Specifically, we use random horizontal flips, small rotations, and shifts. Like brightness and contrast changes, we resize the inputs to 64 multiply 64. This helps the model perform better on unseen images. So with these techniques, the training becomes more stable and validation performance improves, like as you see in the graph. Next. And finally, This is our experimental result. The perform improves from a simple CNN to DenseNet and then to ResNet 50, showing the advantage of deeper feature extractor. So more importantly, data augmentation further improves the results. So the accuracy increases from 98.99 to 99.29%. And we get the best F1 score, which indicates better robustness and generalization. Precision and recall stay balanced. So there's no strong prediction bias across the defect classes in our dataset setting.
Um, in this slide, we explain our ball level decision strategy. The rest bounding box indicate confirmed defects, while blue bounding box indicate low confidence spec. A ball classified as scrap if at least one open or short defect is confirmed. Otherwise, the ball is classified as part. Uh, spec reasons are still visualized for many manual reviews. This slide shows a scrap example. We prevent temp image, tag image, Xor result, and finally inspect result. Since one open and short defect detected, so this board is reject defect label bounding box coordinates are also recorded for our reporting. Uh, this is slide so another scrap case, but both confirm defect and spec reason. Blue box indicates spec defect with lower confidence. Also, some reason only spec the presence of a confirmed open defect as sufficient to reject the board. This exam demonstrates how the system can supply uh, reliability, reliable detection from uncertain reason, reduce for alarm while maintain safety. This slide shows the Phuc exam because there are no open or short defect. Is it? Um, Now I will move to conclusion of presentation. In this work, we propose to study PCB inspect system. The system use Xor-Based reference comparison for the localization defect, followed by CNN-based classification extractor. This design significantly reduce computation compared to a full image deep learning approach, while still achieve accuracy part of scrapball level decision. About our limitation thesis, we are depend on high quality temp image and the system not fully optimized for real-time processing. Mm, in future, we will improve robustness under noise and alignment. Um, use the lighter CNN model for fast interference. It's tend to FPGA oriented processing and decision method for real-time PCB inspection. This is our reference uh, we use for our graduation thesis, and I would like to we would like to thank you very much for your attention. Bài thuyết trình của nhóm em đến đây là kết thúc. Xin cảm ơn thầy.